Okay, Hadi, you can start.
Okay, hello everyone. I am Muhammad Al Hadi Hashim, and I'm gonna today present about direct contact membrane distillation. So first of all, let's talk about water scarcity. We are now actually living in a fresh water problem nowadays due to population growth, due to the economical and industrial advancement and growth. And for this reason, it is expected, or the studies show, that annually the need or the demand on fresh water is going to be around 2%, which is a very big number considering the resources that we have. And also it's expected that about 1.8 billion people are going to be affected by this water scarcity. For this reason, there is uh, all the people, all the countries are trying to have a sustainable water source for everyone to have, for humans to have, and we have to take into consideration that also plants, agriculture needs water as well. On Earth, we know that water is abundant, but only 3.5% of the total water on Earth is fresh water that we can actually use. But 96.5% of it is salty water from ocean. Now, in order to solve this problem, it's either we decrease our water usage, which is impossible, or try to make salty water fresh water for us to use. Here comes then the water desalination techniques. And this is a general scheme of the desalination process. It starts from part one, taking the water from the sea and mechanically filter it to remove solid waste. After that, it is pre-treated for any microorganisms or other contaminants. Then part three is the desalination part, where we are more concerned in. The desalination part is the part where we turn, or to get rid of the salt, turning it into fresh water. This is the world's largest desalination plant in Saudi Arabia, and its capacity is about 800,000 cubic meters. So it is extremely important to work on water desalination for the future. The desalination techniques or technologies that are available, industrially available now, are divided into two main parts: thermal desalination and membrane separation desalination. Thermal desalination is highly developed, highly used in countries in large scale, and they include multi-stage flash evaporation plant, which is MSF, and multiple effect distillation, which is MED. Both of those and any other thermal desalination process require heat, and for this reason, it is really energy demanding. While membrane separation desalination techniques that include reverse osmosis, which is the most commonly used one, requires no heat, it just requires high pressure. So it also needs a significant amount of energy. And also we have the technique that it is promising and being developed nowadays, which is called membrane distillation techniques. It is still in the research and development stage, but it is a promising technique. This is a graph of the energy consumption and requirements for different desalination technologies. It is obvious that MSF and MED, which are the thermal desalination techniques, require a lot of heat, a lot of energy, while reverse osmosis or any membrane distillation process requires less energy. For this reason, it is important for us to start to develop membrane distillation techniques to be able at least to operate them with low energy and low cost and less environmental impacts as well. Membrane distillation technology as a research, it is being developed through the years. The people and researchers are really interested in this technique, and we can see that the number of papers published regarding the membrane distillation development and application is extremely increasing and rapidly increasing. And mainly the research is around either increasing the flux by changing or enhancing the membrane or the module of the process, the energy consumption, trying to implement renewable energy. We're going to talk about that later, and decrease actually the operation cost by decreasing the energy demand or using other possible energy sources. So membrane distillation's advantages are, as we said, lowering the operation heat because it requires less heat than conventional heat techniques, requires also less pressure, which is less than that of the RO, reverse osmosis, which is also membrane separation technique, but not membrane distillation. For this reason, it will decrease the energy consumption of the main technique. In theory, 100% retention of this membrane should be achieved from volatile contaminants because this technique not also a technique for desalination. It can be a technique for removing any desired contaminant from water, and this is extremely important. And which the most important part of this is it can be integrated by renewable energy. Why? Because simply it requires less energy and less heat and less pressure. So basically, renewable energy or waste energy can be used in this technique. So many types of membrane distillation techniques are there. DCMD, which is direct contact membrane distillation. We have SGMD, VMD, AGMD. All of those are under the same title of membrane distillation. We are going to talk about DCMD, which is direct membrane distillation. This is the main scheme of the membrane distillation. We can see that we have a hot channel and a cold channel. They are going to circulate in a module. The hot channel has salt in it, so it's a salty hot channel, and the cold one is the fresh cold channel. Everything is happening inside the main module. This is the main module inside. You can see that you have on the left, you have a hot feed, including an ACl or salt. The left side includes the cold permeate, which is a fresh cold water. In between, we have a membrane. What is this membrane? This membrane is designed to allow only and only water vapor to pass, but not allowing anything else. So even water is not able to enter the membrane due to a property that is called hydrophobicity. We're going to talk about that. But mainly this membrane is designed only to allow vapor to enter. So when vapor is entering the cold permeate, it will condense and be collected. So, and on the left, on the right, you can see the temperature profile where the temperature starts on the hot channel and the cold channel is of low temperature. The membrane in between should exhibit a proper characteristics to avoid heat transfer, have a very good mass transfer to have an efficient desalination. The operation parameters for the CMD are, first of all, yes, temperature. So the temperature difference between the hot, salty feed and the cold permeate or cold fresh permeate. This plays a very big role in the efficiency of the DCMD, the flow rate on which both are circulating, the feed properties depends on what kind of contamination we want to take. Here it is salt, and membranes properties, which is pore size, thickness, and hydrophobicity. This is the last one is extremely important and requires a lot of development. Some of the limitations of the DCMD mainly are the low permeate flux compared to other techniques. So the flux is less than other techniques. This is probably due to it is still in its early stages, this technique. So it requires a lot of research in order to have a better efficiency. Heat loss, mass transfer resistance, temperature polarization between the membrane and entrapped vapor molecules in the pores. This is the main problem, and it actually decreases the efficiency of the desalination significantly. Poor wetting affects the productivity of the MD system, mainly when the membrane is in between two different fluxes, which is hot and cold. The membrane tends to fail if it's not a proper membrane, and then it will have a wetting stage. When it is wet, the membrane, it will allow the salt to or if you want, it will allow the two channels to mix together. Then the CMD is not working properly. And because it's not, this technique is still juvenile and it's early stages, the equipments are actually expensive, because more research, more money, more investments will lead to this technique to be better. You can see here some examples of the activity or action of commercial membranes in VCMD. If you look at the right, the salt rejection, you can see that the salt rejection is approximately 100. So it's a very, very perfect membrane for desalination. It can has a very high amount of rejection. And if you see the flux variation on your left, you can see that is stable. So it is actually encouraging, those results are encouraging for scientists to proceed further in this research. The membrane properties required in this technique are, so first of all, hydrophobicity. What is hydrophobicity? If you look at the image down to your right, you can see a membrane that has water droplets on it. This water droplet is basically the membrane is not allowing water to enter. So, or the membrane is not sucking the water in. So for this reason, the membrane is hydrophobic, or if you want, it has a phobia from water. This is the main reason for this name. It hates water, so it won't allow water to enter, but it will allow water vapor to enter due to the other property, which is called porosity. The membrane should be highly porous in order to allow vapor to enter, but not water. And the maximum pore size for it should be no more than 1 micron, the maximum pore size. The thickness, then, it will play a very big role because of the mass transfer. The vapor should enter easily to the other side, so it should have a low mass transfer resistance, and the membrane itself should be strong. The conductivity, because we don't want heat to be lost, so we expect the membrane to be relatively low bulk conductivity but high surface conductivity in order to aid heat transfer that is going to aid mass transfer as well. Liquid enter pressure, when you say liquid enter pressure, it is linked to hydrophobicity. It should not allow the liquid to pass through it. So it should be high enough to avoid wetting, but not so high to prevent water vapor from entering. And the most important one is thermal and chemical stability. If the membrane is not thermally stable, it will collapse under heat difference. And because we are removing contaminants, so we expect the membrane to be chemically resistant. One of the most interesting techniques to produce membranes is electrospinning. Basically, what's happening is you put a polymeric solution in a syringe, and you have a high voltage power supply that you put it on the head, a metallic head of the syringe. On the other side, you have a collector, a metallic collector. Due to this potential difference between the spinneret, which is the head of the syringe, and the collector, the polymer from the syringe is going to jump to the collector, forming nanofibers in the way. Sorry. So what are the parameters for electrospinning? TCD, which is dip or the spin rate you can see, to collector distance, concentration of the polymeric solution. It should be mentioned that the polymeric solution is different from other polymers. So for example, you can use so many different polymers according to the application that you want to use. But polymers are of different kinds. We're gonna talk about that later, but let's talk now about the parameters of electrospinning. Mainly what affects electrospinning, what affects the fiber production is TCD, which is tip to collector distance, the concentration of the polymeric solution, flow rate on how much you are pushing the polymer out, the voltage difference or the high voltage power supply, and the duration that will affect the thickness of the membrane. The advantages of electrospinning are, first of all, it's very, very high porosity. This means that it is suitable for DCMD membranes. We can control the pore size. We can control even the fiber diameter. We can control the morphology. It's has extremely high surface to volume ratio. As we say, it is of tunable porosity and possible to control the nanofibers compositions according to the application that we want. The types of polymers that are going to be used to produce the membrane can be divided into two parts: thermoplastic polymers and thermoset polymers. Mainly in electrospinning, we use thermoplastic polymers. Why? Because thermoplastic polymers are the type of polymer that can be easily dissolved, and mainly the word thermoplastic is then when you heat the plastic, it can be shaped or reshaped, and when it cools down, it solidifies. Basically, it's the typical plastic that we know. It can be easily dissolved in chemicals so that we can produce nanofibers out of it. It's easily recyclable to other products, but it is relatively weak and thermosoft. It is one of the main characteristics is it will be soft when it is heated. This is a problem because we are dealing with a membrane that is subjected to heat. For this reason, we have another kind of polymers. It's called thermoset polymers. They are cross-linked polymers that cannot be melted, nor dissolved, nor reshaped after curing. So once it took the shape, it cannot be changed. Even if you raise the heat, it won't deform. It exhibits a very high strength and thermal stability. In electrospinning, thermoset polymers are not used because we cannot dissolve them, because mainly we have to produce a polymeric solution. So for this reason, I am suggesting a modified electrospinning machine where we put a UV lamp or heat gun. This is to cure the polymer. And in the polymeric solution, we use a thermoset polymers. Mainly when you say thermoset polymer, you have to use a resin and its hardener. The resin is the polymer, the hardener is the chemical substance that cross-links the polymer. It requires either heat or ultraviolet, or it can be chemically. So what I'm proposing is, upon producing the fibers, before when the fibers are being produced, we put heat or UV on it so that it cures in the way and could be collected, then producing a nanofibrous thermoset membrane, which is, I don't think it is being done before. After we produce the membranes, we have to characterize them because we have to know the information, the data of the membrane to see if it's suitable to be used in such applications. Porometer is the machine that we use to measure porosity and pore size distribution. SEM is used to measure the fiber diameter, the morphology. Even we can use it to measure the thickness of the membrane, but also we have another machine that measures the thickness, which is thickness gauge. And optical tensiometer is a machine that measures the contact angle. What is contact angle? It is basically we measure how much the membrane is hydrophobic by putting a drop of water on it. So contact angle is used to know the hydrophobicity of the membrane. What is the novelty of what we are doing? Basically, we are modifying a pre-existing machine into a machine that can produce a a membrane of different properties with different kinds of polymers, which is thermoset polymers, to produce thermoset membranes, and actually producing the thermoset membrane and characterizing it and using it in DCMD is a new idea, and it's a novel idea. So as a conclusion, traditional desalination technologies are expensive and really energy demanding. So for this reason, we are proposing MD or membrane distillation technologies that are very promising and promising alternative, yet it's still in the research and development stage. DCMD is showing a very encouraging results for water treatment, and electrospinning is an easy and effective method to produce membranes for DCMD, but electrospun thermoplastic membranes need modification to have an excellent performance in DCMD due to their limitations. For this reason, an interesting approach is modifying the electrospinning machine to produce thermoset nanofibrous membranes instead of thermoplastic ones of high strength and thermal stability. For future work, it is convenient to scale up the electrospinning production. If we want to talk about industrial DCMD, we can use another membrane fabrication technologies or techniques such as phase inversion. We can even modify the membranes by adding nanoparticles for it to exhibit a proper properties for DCMD, and we should try to decrease the thickness of the membrane to decrease mass resistance, mass transfer resistance for the DCMD to have a better efficiency. Thank you so much. If you have any questions, I'll be happy to answer.
Thank you a lot, Hadi. It's a very original and nice application. And we have seen it's very related to the course through technologies used and the use of energy also. So thank you for your presentation. To start with, dear students, do you want to ask any questions for Hadi before I start? Yalla, any question? Okay, Hadi, can you move please to the beginning of the presentation and go down to tell you where to stop on which slide? Hadi, do you hear me? Okay, it seems Hadi is disconnected. Let us wait for him to enter again.
Professor, quick question in the meantime.
Yes, tell me.
Should we submit the PowerPoint presentation on Moodle as well?
Yes, it would be better. Yes, of course. Once it's ready, submit it. It's fine if you take a little bit more time for المهم PDF report تكون already submitted.
Yes, it's already submitted.
For the presentation, once you are done with it, submit it على نفس ال submission.
Okay, thank you.
Already we have 2 groups for next week. In case any other group wants to present next week, let me know. Meanwhile, do you have any question on chapter 3, on the videos you covered?
Sorry, Doctor, the internet is connected, so I didn't know if
Sorry, your voice is lagging a lot. Can you please type your question in the chat? Hadi, are you with us again? Hadi, do you hear me? Hadi, please share your screen again. طيب, Hadi is trying to reconnect. For the person who was asking for the question, can you please repeat or type your question in the chat?
I think the person was Hadi. He wasn't asking, he was just saying that he got disconnected.
Sorry, Maurice. ما بعرف ليش the voices are not very clear. It might be a connection problem. Please type your questions in the chat. It will be better. Do you hear me well at least? Do you hear me well?
Yes, yes. Me, I can hear you quite well, Professor.
Okay. Me too. So it seems there is some connection problems. This is why we have lagging effects.
Doctor?
Oui, yes?
Sorry, I have a connection
It's
problem.
fine.
ما عارف إذا حدا سأل أو شيء. I was
No.
waiting questions وقطع الإنترنت وما عرفت.
Yeah, it's fine. Hadi, you can share again.
For the questions?
Yeah, for the questions. I want to ask you some questions.
Yeah.
Yeah. Okay, go please to the beginning of your presentation. Try to put slide numbers, guys. It will be easier than to ask you questions. Go down, Hadi. Go down. Stop. This slide.
Okay.
Yes, this one. Can you just
Yes.
give me a brief description of the difference between these four systems presented here? What
Yes.
is? Yeah.
Yes. Basically, DCMD, the permeates are in direct contact with the membrane. But
Okay.
this is called DCMD. So the permeates are both liquid and in direct contact with the membrane. This is why it's called direct contact membrane distillation. While SGMD, the permeate is a sweep gas. It's called sweep gas membrane distillation. So instead of having liquid permeate, cold liquid permeate, we have a gas passing through.
Okay.
To collect the fresh water, while VMD is vacuum pump or vacuum membrane distillation, similar to sweeping gas, but they put a vacuum pump to enhance collecting the water vapor from the membrane and from the hot feed, while AGMD is called air gap membrane distillation. The membrane basically is in between the hot feed. On the other side, you have an air gap between them, and then you have a coolant.
Okay. What is the main advantage of DCMD over other configurations? Why you selected to study this system and to improve it?
Yes, DCMD is a straightforward module. It requires no other machinery. Plus, DCMD, you can collect the water vapor straight to the mainstream. But it has disadvantages such as heat transfer. For example, the heat transfer, because the membrane should be insulated. insulation.
Okay.
So basically, the membrane, when you put it in between cold and hot feed, the energy will be lost.
Okay.
But what I have proposed, I talked about DCMD, but the proposal that I have done, it is producing a membrane. This membrane not only can be used in DCMD, no, it can be used in all the membrane distillation processes. It's not for DCMD, but I have talked about DCMD because we have the apparatus at AUB, and I have actually worked with DCMD, and I know everything about it.
Okay. Great.
But
Can you
mainly
move?
the membrane I'm talking about can work with any membrane distillation.
Okay. Can you move please to next slide?
This one.
Okay.
This one.
Yes. So you are
Yes.
talking about two sides, hot and cold. So here you need a
Yes.
source of energy. هلا, already you just could have added a section how we can implement like renewable energy to the system to increase its efficiency instead of using, let's
Yes.
say, a heater.
Yes. Actually, energy like renewable energy or waste energy, it's not for increasing the efficiency. It's more like having a better source of energy. So it's a greener technology. It is not going to affect the efficiency because the efficiency of removing salt is inside the module.
Yeah, I
But
know this. Of course. I'm saying the overall efficiency of your system. Yani your system
exactly,
here, I'm not talking about the desalination efficiency, but whenever
yes,
you do the design of any engineering application, your
yes,
energy sources, if you can replace them by renewable energy, the total energy consumed to perform your operation will be then reduced as a cost, I mean.
exactly. Yes,
So
so
in
either
your
waste energy or renewables.
So in general, did they implement renewable energy or they prefer to use heaters to not have to have a continuous feed of energy?
Basically, yes, because you should have a continuous desalination process if it can be industrialized. If there are two kinds of energy that we can collect from the sun, we know that we can either to be PV or simple heaters. Both can work. So either I can take the electricity straightforward to the heater, or I can heat the and they have done that before, especially in Saudi Arabia. I have included that in the paper.
Okay,
They have done that in Saudi Arabia, and it shows a very good, promising results. But again, because this technique is still in its early stages, there are so many complications. The major complication is in it actually failing of the membrane. For this reason, it is important to talk about the membrane, prevent the membrane to fail.
okay, okay, great. Okay. Now concerning, can you move down, please? Okay, stop.
Yes.
Previous slide, please. Okay. Can you talk more about the comparison of PTFE
Yes.
and the other configuration for flux variation and for salt reduction?
Yes. Basically, PTFE, polytetrafluoroethylene. It's a polymer called polytetrafluoroethylene. This polymer is extremely hydrophobic, has a very, very good tensile strength. This is a commercial membrane that we have bought, and we have done a benchmarking for it. It showed a very stable salt rejection and very stable flux. We at AOB tried to mimic this. PTFE was not a nanofibrous membrane, was not done by electrospinning. The other membrane, which is M16420, is a membrane that we have produced using an electrospinning that we have built at AUB using a polymer called PDFHFP, which is polyvinylidene fluoride cohexafluoropropylene. It's also a very strong polymer, extremely hydrophobic, and it showed a very promising results as well. So this is a comparison between those two membranes, and they showed both. We were able to have a similar salt rejection to a membrane that is commercially available.
Okay, thank you. Thank you, Hadi, so much.
You're welcome.
Very nice work.
Thank you.
Dear students, do you have any questions on this or for Hadi or concerning chapter 3? Okay, I will assign for you new videos for 3, and we'll do some practice also together, maybe next time or the one or just next week, the week after. Okay, so please try to not delay your work on chapter 3, because we need to do some practice together on it. And for the exam, as we discussed before, it will be within the first week of April. Now we'll set together a date. We'll talk on the group to set a date for the exam, okay?
Okay.
Any question before we start? Okay, see you next time. Bye-bye.
Thank you, doctor. Thank you.
Welcome.
Bye-bye.
Bye-bye.